Hello, everyone. This is going to be Lab 12 for R. What we're going to be talking about today is simple linear regression. And the example that I chose today has to do with a little plant called Iris setosa. Let's see a little bit how it looks like. Yeah, that's a little plant here. And what we're going to try to do is we're going to try to create some sort of linear regression that connects the width and the length of that plant. I have a data set for you. Let's first load in the packages. I'm going to be using tidyverse and OLSRR. If you're using R Markdown, you should also start with knitter and cable extra. Go ahead and load these. And of course, my favorite easy package is there. And what we're going to do is we're going to start with the data set. Okay, let's try to load that in. For some reason, this did not pop up here. I'll make sure that it appears. But the data set I'm using, as I said, is the Iris setosa. And so let's try to read that in. Oops. Let's try to read that in. Okay. Let's also make sure that we're in the right folder. Okay, so when we read it in, you'll see that it has 48 observations. It's just the width and the length of the petals of this plant. So what we want to do is we want to create a linear regression between the two. Okay, the fitting of a linear regression, the code basically is very, very simple. You need to use the LM linear model, basically, and then you need to tell it which output variable to put first and which one to put second, and then what data set to read it from. It is customary also to save it as something, let's call it the model here. All right, so if I run this one, it's going to quickly create a model that has a lot of things in here. If you open it up, you see it's got a coefficient, residuals, effects, all sorts of things. We'll explore that in a little bit, but really it's just a one-line command. Note the syntax here. This now technically is going to be my output variable, and this is my input variable. I could have flipped them around and it still works similarly. Okay. Then what I want to do is I want to create some simple plots to see how these two kind of look together. And first, we will try to do the correlation coefficient. We will learn that very, very soon. This gives just a numerical idea of how related these two things are, and the correlation between these two apparently is 0.701, so quite high. All right, so we know that these are positively correlated, and doing a linear regression actually makes sense. Okay. Then what I want to try is I want to try to review a little bit the model. So let's run it again and do a little summary, or just run this line that will do a summary of the model. And so the summary function, we've seen it before. You can do summary of a lot of things. If you do summary of a data set, you get like the summary statistics. But if you do a summary of the model, what you end up with here is the basic things that we need. So you need some idea about the residuals. You need the estimates of the coefficients of the linear regression. So this is going to be the constant term, and this is going to be the coefficient of length, as well as some sort of standard error for these, a t-value. We will learn what that is in class, and then the probability of that corresponding t-value, basically an idea of whether or not this coefficient is statistically significant. You also get the residual standard error, you get the R squares and the adjusted R squares, which we're going to be focusing on, the corresponding F statistics of the ANOVA, and the corresponding p-value of the ANOVA. All right, so if you do a summary statistics, you get all the information here. But what I want to do is I want to explore this a little bit further, and I want to create what we call the diagnostics of it. And this basically will plot the residuals of the linear regression. We'll extend that a little bit further, but this is something that you definitely do right after you do the model, right? And we'll get back and explain what this means and whether or not the residuals here, have all the appropriate properties that linear regression wants. Okay. But typically with just these codes, you just get a good idea of the linear regression. It's very, very simple, like 5 lines of code, and you got the whole thing. Right. Okay. Let's understand what happened here. First of all, let's explore a little bit the model. Let's figure out what type it is. If you use the command class model, it's going to tell you that this is an LM model. See down here, it's an LM model. And if you're looking at what type of information is in there. You have the coefficient, residuals, effects, and everything, right? Don't forget that you could always like double click here and see, you know, what is in here. It's a list of lists basically, right? And the coefficients are right there with various things attached to them. The residuals are here and so on and so forth. Let's try now to see just the coefficients. These basically, remember, are the numbers that you need to put in your regression equation. And so what you need to do is you need to take the length and multiply it with 0.744. And then to that, you add the intercept. So in this case, subtract 0.286, and that will give you basically the width, all right? Besides the coefficients, you could also get some confidence interval estimates for these coefficients, and you can do that by just doing confidence the model. So there are a lot of functors that you can apply to the model and get various things, right? So this gives you an idea of the confidence interval for the intercept and the length, and the variable for the coefficient of the length. Okay. So let's try now to do the classic ANOVA table. And it's very easy. You again have your model, and then you apply the functor ANOVA to it. And let's also save it as something. Let's just call it ANOVA table. All right. So ANOVA, the model that you've already run, is going to create the ANOVA table only. And there it is, right? We see down here that the p-value is much smaller than 0.05, so we reject the null hypothesis. This implies that beta 1, the coefficient for the length, is actually statistically significant. The length can be used to explain the width or to predict the width, right? Still, you need to know, the rest of the cells inside this ANOVA table, but that's how you implement it in R. All right. Once again, don't forget that the null hypothesis for this ANOVA table is that the coefficient inside in front of the length is 0 versus it is not 0. So in this case, we say that it is not 0. In other words, length can be used to predict the width. Okay. Now, we also want to get the adjusted R squares and the root mean square error. And this little command here, this little function just outputs the root mean square error. I didn't find like any, immediate way to do that. So, we just created this very, very small command. First, we save the sum of the model as A. And now A, notice it has a bunch of things here. It's a whole list of stuff. So if you just do A and then $R squared, this way you just get the R squares. All right. And if you want to find the adjusted R squares, you just do the same thing, but now instead of R squared, you do adjusted R squared, and there it is. And now the root mean square error can be found by, taking the residuals, using the coefficients, and then there's this little formula there, right? We saw that in class, but if you run it this way, you're creating a function that computes the root mean square error. And so then here it is, 0.27. Again, remember, the smaller this one is, the better. The larger this one is, the better. Okay. There are no thresholds here, but you want the root mean square error to be as small as possible. All right. Now, the next is just, another little command that will put everything into a nice, neat table. Just use this little piece, basically. And I promise I'll fix that. So here, if you want to create a nice little table as a data frame, basically, here you go. Maybe you want to output that and save it somewhere and then copy paste it somewhere. This can also be saved as an Excel sheet, and you can get all this information and attach it, let's say, to a write-up that you have. This is just for show. You don't really need this. Now, again, in this table, we have various things like the parameters, and you can use those just like I said. You just plug them here, and this formula gives you the estimated width given a length on average, right? And we know how to read this. A 1 point increase in length introduces a 0.7444 increase in width, right? And if there is no length, then the approximate width is negative. So this doesn't make sense if there's no length, right? Because these properties, these are lengths and widths of petals. All right. So what we want to do now is we want to create some regression graph including, all of the information that I have in the linear regression. The first thing that I want to do is I want to have a little function here that creates the equation of the linear regression in a format that you can then use to put into a graph. Okay, so let's look a little bit into this code. What it does, again, it creates a little, character here called equation 1, and all this is reading the model and it's keeping the various coefficients, right? The A, the B, and the R2. And then it saves everything as an expression. This is a very specific way in R. If you see equation 1, it looks, all sorts of weird, like it looks like this. And as you can see, this is the regression line in a sense, and these are the R squares. Now, it looks very weird here, but when I plot it in ggplot, it's going to look very nicely. And so what we need to do then is we need to take the data set that we have that only has length and width and extend it with what we call the predictions of the model and the residuals. All right, so the residuals is very easy. We're going to talk about it in class. The predictions are basically the expected value of y given a certain x. We've talked about that in class. It was that mu of y given x. So when we created, these two are saved as predictive model and residuals of model. So what I'm going to do is I'm going to run this line, and I will take those predictions and those residuals, and I'm going to add them into my data sets. All right, so I'm just extending iris by adding, as you can see here, the predicted values and then the residuals. All right. And I need to do that because when I create the graph later on, I will need those predicted values. And so for this graph, let me run it and I'll show you what's going on. This is a ggplot graph that works with this. Note what we put here. We put the data set, we put the length as x value, the width as y value. And then we're going to put also all the predicted values here. And I think I forgot something. No. Let's see what's missing here in this little code. Did my copy paste not work very well? No, it seems to be working. Let's see if I run this part only. Okay. All right, so that's how it looks. I'm not sure why it didn't work a moment ago. Let me do it again. Okay, there we go. So what's happening here is you get your linear regression line. You get all of the values for x and y, and then based on how much this distance is from the predicted line, basically how big the residual is, you have the residuals being color coded, right? Red being very, very far and going to black being very close. Okay, so the bands here are also as we saw, the confidence interval for the coefficients will create various lines, and that's what you see here. Okay, so that's one of the graphs that you could be using. And note now here the equation and the R squares. Right? So although the equation, when you type it out, it looks weird, when you put it in a graph, it looks, just like it should be. Okay. So then that's one type of graph that you could be using. And of course, you can save it using the ggsave. So there you go. ggsave regression 1 is going to save it at a safe folder. There's another type of graph that is focusing on something else, a little bit more about the predictions. So again, I'm going to do the prediction and I'm going to extend it now this way. This first line creates a prediction, and the second line is just basically adds it to the iris. Okay. So the iris extended looks like this, right? So when you do the predictions, besides the predicted values for the width, you also get an upper bound and a lower bound, right? So those are saved here, the lower and the upper. And the prediction, the fit is exactly the same as the predicted. I just didn't want to do it again. So I just append those there. Becomes a little bit larger. And so the graph that I'm going to create now has not only the confidence interval for the parameters, but it also has something called the prediction window. So let's see how this looks like. Okay, and as you can see here, you have the again, the same stuff as before. This time they're not color coded. This is the regression line. These are the points, and this is the 95% prediction band, right? And the 95% confidence interval. So that's another one. So it depends on what type of graph you want to create. Both of them are valid. And I save that again using ggsave one more time. There we go. Saves it again in the same folder. And then you can put all of them together if you really, really want to. And this is going to do practically everything that we discussed. It's going to create the prediction bands. It's going to create the 95% confidence interval. It's going to put the value, all bells and whistles. So let's run this one. This might look a little bit, heavy, but it's the most complete thing that you can do. Right, so it's got the confidence interval, the predictions, the absolute residuals, the formulas there. You can put names and titles and all that. Up to you, right? I mean, I don't pretty much care. At least one of them should make it there. Now, when you move to a higher level class, you will explore a little bit more what's the prediction and all. For now, that's not really the purpose of what we're doing. We're more interested in creating this regression line and also putting the confidence interval around it. So as long as you have these two, that should be fine. All right, so again, let's go ahead and save this one as regression 3. And so in terms of like creating our model and reporting a couple of things on it, we are done. What we're going to do now is we're going to check the assumptions, which is very, very important. If you're doing that for, let's say, a project, or if you're working on your homework, you need to mention the linear regression assumptions, which is the linear relationship between the two variables applies. The error terms are independent, they're approximately normally distributed, and they have a common variance, right? So once again, let's do a little quick plot to just see, in this case, the QQ plot of the residuals. One of the things is to test if they're normally distributed. And again, if you look at the QQ plot, they are kind of normally distributed. Maybe we have some outliers. We will check it, okay? So here's one quick code that just plots basically the residuals versus the fitted, just to make it a little bit larger so that you can see it. I tried to do it with ggplot, but it didn't look so nice. So, you can just use this one. And there you go. Basically, in this situation, we want the residuals to be hugging the line of 0, right? Some of them are going to be above, some of them are going to be below. We don't want them to have extreme outliers. And you see the numbered ones are basically a little bit extreme. We'll test them later. And as I said, the variance of these things above and below should not have a certain pattern, right? In this case, it doesn't. Like practically all of them are scattered around the 0 axis. Okay, so this kind of takes care of the, the residuals are not so skewed, they don't have a pattern and all that. All right. What we need to see also is we need to see the Kolmogorov-Smirnov test. Let me also plot this one since I have this code. We'll plot the this will plot basically the QQ plot just a little bit easier to see. And again, we see some outliers. Again, the 41, the 32, and the 46 are probably outliers in terms of residuals. And so the best way to figure out if the residuals fall in a normal distribution is to do some sort of goodness of fit test. And when I was researching this lab, I found a lot of statisticians pointing to the Kolmogorov-Smirnov test as being the most appropriate to test normality of residuals. So from now on, if you're doing this, just look at the KS statistic. The next line, as you can see, is going to take the residuals and it's going to try to see if they fit a normal distribution, utilizing the mean of the residuals and the standard deviation of the residuals. So that's the code to test the Kolmogorov-Smirnov. And remember, again, in the Kolmogorov-Smirnov setting, the null hypothesis is that indeed they come from a normal, and the alternative is that they don't. So when you run it, you get this huge p-value, 0.938. You can assume that the residuals do come from a normal distribution and continue on with your analysis. All right. Then it is a good idea also to create a histogram of the residuals and fit the corresponding normal plot. And this next code will do that for you. And again, this is more or less just for show. If you do the Kolmogorov-Smirnov test, you know or you don't know if they're normally distributed. But look at the graph here. Shows that, yeah, they seem to be normally distributed. You do have this outlier. So you need to kind of like explore it a little bit further. But yeah, I think they're normal distributed around. So it's pretty good. Now, besides the way that we did here, there's a whole package that is called OLS-R that takes care of the checking whether or not a linear model works. As a matter of fact, OLS-R can be used for high-level models. So it is a good idea to just install it there, have it, and use it when you move to, I don't know, 7.0.14. This is probably going to be something that you use all the time. And I found it super useful, so why not do it here? It does the exact same thing. It just has, some of these checking of the assumptions. They are just kind of like streamlined. For example, if you run your model and you apply the OLS plot resid QQ the model, so there's the new factor that exists in the OLS-R. So if you run this one, you just get the QQ plot of the residuals. Wait, let's see, let's run this. Okay, and then let's run this. All right, and as you can see, it just creates a QQ plot in a nice, GG plot environment, right? So this is kind of like streamlined, and it's just a one-line code now. And if you want to test for normality, there's this OLS test for normality. So basically, it's doing the stuff that we did above, but with functions already created at the OLS-R. Okay, so there you go. This creates all of them. And as I said, again, focus on the Kolmogorov-Smirnov. There it is. And finally, you can test the residuals with this residual fit. And when you run it, it creates this nice little plot. Again, same stuff as before. And all of these have various arguments, and they're kind of like streamlined stuff that we did above, right? I don't have any preference. You can use either or. It's just that if you do it by hand, it's easier to customize. If you do it with the OLS-R, you just have to basically learn this package. But it does the exact same thing. And there you go. Here's even the histogram. But notice that this histogram is with less box plots like the other one. So you need to figure it out in a sense, right? So the other one, the one that I showed you before, a lot of customization. This one, a lot of streamline, whichever one you want. Okay. So right, that's all I had to say about the linear regression. Now, as I said, we're focusing here on explaining linear regression. We're not focusing on predicting with linear regression, but if you want to, there's this link that you can find in the notes that takes you to the STHDA site. This is very, very useful. I found a lot of good information over there about applications of statistics, especially with R. So if you want to review a little bit about how you use linear regression to do prediction, you can click on that. Okay. But that's not something that I will check in this class, maybe in higher level classes. All right. Okay, so that's all about this lab. If you are using linear regression for your project, make sure that you follow along with this and cover everything that is discussed here. All right. I guess that's it, and I'll see you soon.